Okay, so now we are on section that's 7.2. So this 7.2 is the small sample estimation of population mean, right? So we've done that of the last sample. When n is greater or equal to 30, we are dealing with last sample. And based on this, we know how to construct the interval estimates. Note that we are using the ZF over 2 there. But here, when you have the small sample, we could use the Z alpha, or we could use another distribution known as the student T distribution. So that is the two different things we have to consider here when getting to know which kind of distribution to use in order to construct your confidence interval based on the sample size given. All right. So for section 7.2 deals with a small sample. So the student is actually a continuous random variable, just as the Z distribution or the standard normal. But just that the difference is that it has heavy tails. The heavy tails means that the curve, the tail of the curve doesn't touch the S axis immediately. Okay, but with the normal curve, the tail touches the S axis immediately. That is the difference between the T and the Z. Okay, all right. So, but we will get to know what we mean by degrees of freedom. So we know what sample size is. If you have your sample size and you subtract one from it, we call it the degrees of freedom. And based on these degrees of freedom, we get different curves for the T distributions. Okay. So since for T distribution, we want the sample size to be less than 30. But if the degrees of freedom keeps on increasing, you realize that the T distribution becomes the standard or the Z distribution. So you compare the differences. You realize that when the degrees of freedom is 5, this implies that if you had a sample size of 6, okay, you subtracted 1 from it, then we get 5. So you get to know, so we have the distribution as this, and the tail doesn't actually touch the S axis. But as the degrees of freedom keeps increasing, you realize that the tail keeps touching what? This is the tail for the degrees of freedom. 25. This implies we have a sample size of 26. Okay, although the sample size is less than 10. So if we keep on increasing the sample size, then the T is exactly what? Or it's approximately the Z distribution. And the same approach that we learned from 7.1, the same idea is what we're going to learn here. Just that here we are dealing with a small sample, and instead of using Z alpha over 2, we use T alpha over 2 if we have to use that. And so these are the properties. It has the same properties as the Z, and as the degrees of freedom increases, as the degrees of freedom increases, the T distribution approaches what? The normal Z distribution. So after 30 degrees of freedom, this implies we have 31 sample size or more, then we are approximately doing the standard normal, just as we've done already. So this is how we do it. Although if you have n, that is small, but if you have our sigma, the population standard deviation is known, we still use the Z. But if n is small and the population standard deviation is not still known, then we use the T. Okay, and since we don't know sigma, we use S to estimate it. Although, are we okay? And the degrees of freedom, note, is n minus 1. Okay, so this is the small sample consideration. And now we construct, so now our E could be T alpha over 2, then we multiply by S over square root of n, or it could be sigma, Z alpha over 2 sigma, just as we know already. That's the E, the margin of error. Okay, so let's consider some example and let's construct it. So here we have a sample size, n is 15, so n is small. But if we have n is small, do we know the population standard deviation? But we realize that, okay, we have our S bar here. So these are the things we are noting. And we have sample. So the sample standard deviation is S. Instead of population, we use a sample. So note it well. It's 14. So this implies that we are using T alpha over 2. So how do you construct? So we have to construct a 95% confidence interval for the population mean. For this one, we don't know. If it was Z, then we know that 95, we get the Z alpha of what? 1.96. But for T, we don't know. But maybe you can also calculate the things that you might need there. So these are the questions we ask ourselves. The question is being brought down here. Is it normally distributed? Is it large or small size? Do we know the population? So, okay, so the check is that we have n to be small. We have sigma not given, so we use the T interval. So if you use your calculator, the calc, you click the start, you go to what? Your test, then you choose what? That of the t interval rather. Okay. So in case you have to write it mathematically down, so we are going to have S bar plus or minus. We have t half over 2. The degrees of freedom is n minus 1 instead of df. Then you write s all over square root of n. Okay. So in case you want to work it manually, this is how you go it. But let's use the calculator first, and let's work it manually as well. Okay, so we use the calculator based on the information given. Okay, so we click on the stats, we go to test, then we choose, this is t, then you have t, so the t is the 8, so t interval. So it's going to ask you S bar. So our S bar was given to be 35, our sigma S sample standard deviation is 14, and our sample size, that's the n, is 15, and the confidence level is 0.95. Okay. So this gives us the interval that you wanted to get. Okay. So that is that. This is the interval that we see for there. Okay, we can do it also manually. So you have to find your T alpha over 2. What is alpha? Alpha is 5%. Alpha over 2 is 2.5. It's 2.5%. That is, so in all, this will be alpha plus or minus T alpha 0.025. And n is 15 minus 1 is 14. Then we have our s, and we have square root of what? And so we find the value for this. How do you find this? Using the table. So you go back to the table and you choose the t, you use the t table. So we have to find t alpha over it. So we have here to be what we want. So this should be your t alphas. Okay, so choose your T alpha over 2, that is 0.025. Then what is the degrees of freedom? So this is the degrees of freedom. We are using degrees of freedom 14, right? So where do they map? Where do they intersect? Realize that if you come down, they intersect at this point. Okay, so this implies that T alpha over 2 with degrees of freedom 14, we get the T alpha over 2 with degrees of freedom, with degrees of freedom 14 to be 2.145. Okay. We can also use our calculator to get it. Okay, we use the inverse. So you click the second, then you go to inverse t. So the area is your half over 2. You know that is going to give you the negative side. So we choose the positive. So what is the area? Half over 2.025. The degrees of freedom is 14. Then we paste. So it gives you minus 2.14. So this runs it to 3 decimal place. So if you run it to 3 decimal place, it's the same answer. But this gives you the negative side, but convert it to the positive side. So that is 2.145. Okay, so that is that. Okay, so we do the same examples, but note it well, the things you need to note. So, but here we are giving n is small, which is 19, but the sigma is given, so we have to use z rather than t, because that's the population. It wasn't sample, so population is given, population. So use your z, otherwise you get confused and get it wrong. So use the z interval. Then, so these are the things you have to note for the small sample estimation of the population. Then you can interpret it as well. But there are things you have to note. Okay. There are things. So let's jump to question 5. So in this question, you do your 96% confidence interval by, so n is 25, you use t, and we have the sample standard deviation. Okay. So we use t. So these are the two things you have to note. So after calculating it, we were asked some questions. You have to construct a 96% confidence interval for mu if the sample size is 10. So with the same confidence interval, when the n is 5, we had an answer. We have a confidence interval. But as we decrease the n size, how does decreasing the sample size affect the margin of error? So if we decrease our sample size, what happens? You realize that we actually widen what the confidence interval. So from this, So from this, we increase just to what? To this. So if you have more data, then we reduce the error. That's the information. If your n is large, you reduce what? Your error rule. If you have less data, then your error will increase. But if you have more data, your error will actually what? Decrease. And if the error decreases, then we add more to the points. If the error is small, because this is the interval how it's being plus or minus e. So if this is small, then you add little to this and subtract little from that, then your interval is narrowed. But if this is big, then you have to add more to this and subtract more from that, then you widen the interval. So that is the interpretation for that. Okay, but in case you don't have that additional data and you want to use a confidence interval to realize that if we increase our confidence interval, then we are increasing what? Our T alpha over 2 or our sigma alpha over 2. By doing so, it increases our error. So it implies that if the confidence interval is being decreased, then the margin of error is also decreasing because the T alpha over 2 is decreasing. So it decreases the margin of error in an interval. So always when E decreases, then your interval gets narrowed. But if your E increases, the interval gets wider. Okay, so in case we are not using our N and we are using the confidence interval to determine whether our interval is decreasing or increasing, then we know that when C decreases, margin of error also what? Decreases, interval gets narrow. If C increases, margin of error increases and interval gets wider. Okay. So could we have computed a confidence interval in part A3 if the population had not been null? So we are doing this using the population should be normally distributed because n is less than 30 and we can apply the central limit theorem. Okay. The population must be normal for the confidence interval need to be valid. Okay. So note this as well. So in this question, we weren't given the standard deviation, we weren't given the S-bar, we weren't given anything, but we are given just raw data. So you have to estimate your S-bar, you have to find your S-bar, you have to find the sample standard deviation, and you have to know your N. By doing this, you can get your confidence interval. Okay, so this is a raw data approach. In the previous questions, we've been giving them, so we just start by doing it. But this, you are giving just raw data. You start afresh. You get your S bar. So in situations like this, one, you get your what we are interested S bar or what your periods. Okay, but normally we focus on this. And two, you get you get your N, your sample size. So you count the number of data points you have, and three, you get your sample standard deviation. Okay, if you know this, it's just the same as provided. They've been provided the information above, and we know how to get the S bar using our list functions. You can use your calculator to get your S bar. You can get then you are good to go. So that is what we did. Then we constructed our confidence interval. Okay, you are good to go. So since our n is less than 30, n is 10, and the standard deviation wasn't given, we use the t. We use the t. Oh, we use the t. Okay, as you see here. Okay. So now, what happens to the interval as the level of confidence is increased? So if you increase your level of confidence, you know that the interval also what increases. It gets widened because the margin of error has increased. And what would you recommend to us so if you don't know any additional n, because if you know that when n is more, then the error is being decreased and our interval gets smaller. Okay, but we don't know that, then we have to use the C approach. This implies that we have to decrease our confidence level to get a narrowed interval. All right. So that is that for section 7.2. If you have questions, please do ask me or email me. Thank you very much.